recording, and please grab it now.
Yeah, just the one we talked about.
Ready to get started?
Sure.
Awesome. Everyone, thanks for coming out this morning for our rescheduled colloquium. Luckily, we got Professor Brooks Lindsey rescheduled and decided to come back out to visit us. He is actually back at NC State and Chapel Hill. He was a former postdoc here, and now he's an assistant professor at Georgia Tech in their joint Department of Biomedical Engineering. So just like we have NC State and UNC, they have Georgia Tech and Emory University. He's a highly cited and award-winning IEEE author in the space of ultrasonics. So we have a few in the crowd, I think, from ECE and maybe from a few other departments. And without further ado, I'll turn it over to Professor Lindsey to talk about developing sensors and systems for functional interventional ultrasound imaging. So a biomedical topic this week.
Great. Thank you so much, Michael, for that introduction. Thank you all of you for having me today. It's great to be back here at North Carolina State. So like Michael mentioned, I'm Brooks Lindsey. I'm from Georgia Tech and Emory, where I'm affiliated with biomedical engineering and also electrical and computer engineering. And in my lab, we work in developing sensors and systems for functional interventional ultrasound imaging. So I'd like to start off today by talking a little bit about the problem or the clinical diagnostic workflow that we're interested in addressing with the technologies that we develop in our lab. And so the first thing I wanted to show today was this brochure or this poster from American College of Cardiology, where they tell you what to do if you think you may be experiencing a myocardial infarction or what we would call a heart attack. And so it goes through these different symptoms here. It talks about chest pain and these other non-specific indicators of heart attack. And it says if you think you may be having some of these symptoms, don't delay, call 911 right away. So what I want to think about today is what happens after this. So what are the next stages in this process? When, for example, the patient calls 911, they end up at the emergency room, and then what happens from then on? What are the tests? In particular, what are the imaging tests that that person would undergo? And then what information do we get from that imaging test to start the treatment process? So when we think about that process where the person presents at the ER, they're complaining of chest pain, and some coronary artery disease is suspected or some coronary artery involvement, some risk of myocardial infarction is suspected. What is the imaging test that they're subjected to? The first test might be a CT, like we see on the left here. And CT is a non-invasive imaging test that uses X-ray, so it does use ionizing radiation. And using CT, it's possible to image the structure of the coronary arteries. And the question that we're trying to answer there is there coronary artery involvement, or is there something else entirely that might be producing the chest pain or those symptoms that they're having? Next, what happens if on the basis of that CT scan of the coronary arteries, it's determined that the coronary arteries are involved and the person is at risk for myocardial infarction? Well, then they would go to the cardiac catheterization lab or the cath lab, where they would undergo further imaging tests such as catheter-based angiography. So it's important to note that in both of these tests that we've talked about so far, we're exposing the patient to radiation. So the CT would expose that patient anywhere from 1 to 6 years equivalent background radiation exposure. And then when they go to the cath lab, it's an additional perhaps 3 years of background radiation exposure. We also want to think about the types of images that we can acquire using these different types of imaging tests. And so we talked about the CT, which is a 3D imaging data set. And then if they have to go to the cath lab and undergo the catheter-based angiography, then we could acquire an image that looks like this one on the right here. So this is a 2D projection image. And what we should think about is that we're projecting or we're integrating over this complex 3D anatomy to see only this 2D planar view of the anatomy. Again, we're exposing the patient to ionizing radiation when we do this. We're also exposing all the staff in the cath lab. So nurses and physicians, anyone that works in the cath lab, they tend to accumulate about an additional 2 years of background radiation for each year that they work there. So in addition to all those numbers that we've just been describing, thinking about the radiation exposure, there are even more cases that represent challenging or complex cases. In those cases, both the patient and the staff would be exposed to even higher levels of radiation because we have a longer procedure, okay? So if we wanted to summarize all this, then in some of these more difficult, complex cases, the patient might be exposed to an additional 4 to 10 millisieverts per patient. So why is that? Well, we can think about what's happening here is we're trying to route something like route a catheter from the person's arm or the leg to the coronary artery, which is on the surface of the heart that we're seeing here. And what happens if we encounter an occlusion on the way to the heart, or we encounter some tortuous anatomy that's difficult to advance the catheter beyond? It's going to take longer, it's going to require more imaging, and that's more radiation for both the patient and for the staff as well. So the goal of our lab is to not use ionizing radiation, it's to use ultrasound and to develop systems that use ultrasound to reduce or eliminate our dependence on X-ray imaging and ionizing radiation in general. And so the way that we do this is by developing these novel ultrasound imaging systems. And today I'm looking forward to telling you about 3 of these different systems that will work into this clinical workflow that we've been describing at 3 different stages in the process. So the first system that I'll describe today involves the determination of coronary artery involvement. So what happens when that patient first arrives at the emergency room, they have chest pain, and then we said they can undergo a CT. Well, how can we combine ultrasound and CT to reduce the radiation exposure at that stage in the process while still producing a diagnostic quality conclusive image? Next, we also talked about what happens when that patient has to go to the cardiac catheterization lab. And so I will also talk about a new ultrasound system that we're developing there, which is a forward-viewing system for minimally invasive guidance. And here what we're thinking about is when the patient is in the cath lab, how do we acquire functional information? So can we quantify blood flow? Can we say something about the composition of the lesion or about the stenosis itself? And then finally, we'll think about that challenger or that complex case. So what happens if we can't do any sort of procedure? We can't do catheter-based imaging because this catheter device that I'm showing here cannot be routed to the occlusion. So in that case, if we can't get the catheter there, or if we can't even get the guide wire there, and the guide wire is the part that would go through the middle of this catheter and is used to deliver the catheter itself, then it's hard to help that patient. And so at the end of today, I'll talk about our development of a forward-viewing ultrasound-tipped steerable guide wire, which is a smaller device to try to steer around these different occlusions that might be encountered on the way to the lesion or the stenosis of interest. Okay, so if you have any questions, feel free to interrupt. Otherwise, we'll kind of keep going. We'll keep thinking about this process or this workflow, beginning with that idea of what happens when the patient presents the emergency room complaining of chest pain. So how do we non-invasively diagnose or non-invasively determine a coronary artery involvement and risk for myocardial infarction or other major adverse cardiac events? So we know that coronary artery disease is a major problem in the US, but really everywhere. It affects about 18 million adults in the US, which is about 7% of all of us. And separately from that, we have 7 to 8 million people visiting emergency rooms in the US each year in the situation that we've been thinking about where they're complaining of chest pain. So the first goal that we have is just to image the structure of the coronary arteries to determine if that person is at risk for myocardial infarction. So what we're trying to do is simply to make an image of the different major coronary arteries that we see in this illustration here, and to see if we see a stenosis, to see if we see any involvement based on imaging. So there's several different ways that we've already talked about for imaging coronary arteries, and perhaps the most attractive from a non-invasive point of view would be something called CTCA, which stands for computed tomography coronary angiography. And that's just the scan where the person lies down in the CT scanner. The source and the tube rotate around the patient, and we can acquire these CT scans of the coronary arteries. So this is a non-invasive test. It costs about $500. And if there's nothing wrong with the patient, they don't have to stay overnight in the hospital. Alternatively, there's the catheter-based coronary angiography that I've also already mentioned. And that typically does require an overnight stay, and the cost is something like $50,000 to $60,000 per exam. It is invasive. It uses an intra-arterial contrast agent and a catheter. So it's clear which one you would want to undergo, but this is the better test. The catheter-based coronary angiography is considered the gold standard, and so we would have to get this CTCA test performing at the level of CCA before we could send everyone to only a CTCA to either rule in or rule out coronary artery disease involvement. So the challenge here with this catheter-based minimally invasive exam is many of these patients who are sent to the cath lab and undergo this minimally invasive exam end up having a normal result. So 40% of these people are normal in the sense that they don't have any coronary or cardiac involvement at all. So maybe they had a gastrointestinal issue, for example, that was causing their chest pain or some other or non-specific symptoms that caused them to show up. And so how do we get more of these people, like we said, to CTCA instead of CCA? Well, we have to have the right technology to make CTCA work a little bit better, to be able to use CT for coronary artery imaging only. So when CTCA works well, what we would see is something like what we're seeing in this image here. So you can see a coronary artery, and you can see the white arrows pointing to this clear stenosis where it kind of cuts off right there. So there's an obvious stenosis, and that's great. You know, we can see that conclusively with CT, and we want to use CT because CT is everywhere. It's in almost every emergency room in the US, compared to about 40% of the same hospitals. Only about 40% of the same hospitals have access to a cath lab. So on the left of this slide, I have this exact same image that I showed on the previous slide, where we see CTCA working well, right? We see the clear stenosis. But on the right, we have a different CT image of the heart. And here we can see that there's a lot of blurring. There's a strong motion artifact on the left side of this image. And we can't actually see the coronary arteries at all in this particular image. And so this is an example of when CTCA does not work well. And you can see why that can happen, because what we're trying to do here is we're trying to image a moving target, right? So the heart is beating all the time, and we're trying to image these small arteries or these tubes that are on the surface of this moving object. And so the challenge here is, how do we effectively gate the acquisition of the CT scan when we're trying to image the heart? There's basically two ways that we can do that. One is called prospective gating with ECG. So the person can have ECG leads on them, they're lying down in the scanner. And then based on the electrical activity of the heart, then it's possible to only turn on the X-ray tube, only acquire the images at the point in the heart where there's less motion, and we call that the quiescent phase or the quiescent period of the heart, okay? And so that can work, but unfortunately, even using that approach, about 20 to 30% of the scans end up being non-diagnostic and not being useful. And you can sort of imagine how that can happen when you think about, okay, there's a patient, they're stressed out, they're lying in the CT scanner, they don't feel well, they have chest pain, and they don't know what's wrong with them. And then even separately from whatever's going on with the person on that day, many patients also have an elevated heart rate, or they might also have an arrhythmia. And that would lead to some disconnect between the actual mechanical motion of the heart, which would produce the artifact in our image, and the electrical activity of the heart, which is what we could sense with the ECG, right? So there can be in some people a disconnect there as well. So the other approach, if you don't use prospective ECG gating, is to use retrospective gating. And basically that means you just leave the X-ray on for a longer period of time. You give yourself a longer imaging window. And then afterwards you can go in and you can pull out only the good images. And so that gives you a very high likelihood of having a good diagnostic quality CT image of the heart. But you've also exposed the patient to higher radiation with that longer window, okay? So those are currently the two approaches for CT imaging of the heart. We know that ultrasound could be really effective for imaging the heart, like we can see with this image on the left, which is just a B-mode ultrasound image of the heart, echocardiography image. Of course, we can't actually directly image coronary arteries using ultrasound because we don't have the resolution at depth. What we can see, though, is just kind of the bulk mechanical motions. We can see the shape of the heart, we can see the septum, we can see the ventricles. And then if we look at only one plane or one slice through the heart, that's what this red line is showing. And if we look at that as a function of time, that's what we call M-mode ultrasound over here on the right. And so if we look at this M-mode, it's easy for us to identify, okay, there's some time points like right here, for example, where there's less motion, and then here there's a lot more motion. And so if we had something like this, then we would know, okay, this is when you want to acquire your CT images, this is when you want to turn on the X-ray, for example, somewhere in here, but then when you have more motion, you don't want to acquire the image there. So this should work well, right? We just need ultrasound gating instead of using the ECG gating, and we just need to combine the ultrasound and the CT system. Unfortunately, it's not quite as simple as just putting the ultrasound transducer on the person's chest while they're lying in the CT scanner, because if you do that, you get an image on the CT that looks something like this. And so this is a commercial ultrasound transducer, and it's on the chest of an ultrasound phantom. So this is not actually a person. That's why they don't have a heart in there. And you can see some of the streak artifacts that would be obscuring our ability to see the coronary arteries if this was an actual patient. So the problem here is, how do we develop an ultrasound transducer that's CT compatible, or that we could use at the same time the CT images are being acquired, without producing those terrible artifacts that result in the non-diagnostic scan. So I realize some of us here are probably ultrasound experts and know all this, but on the left side of this slide, I'm showing the quick cross-section of a piezoelectric ultrasound transducer. So this is kind of the anatomy of the ultrasound transducer. It's definitely not drawn to scale. You can see we have the piezoelectric material here. This is, for example, like PZT, lead zirconate titanate. This thing will vibrate, and when it vibrates, it produces acoustic waves in both directions. So there's one going out the top, and in this design, in this organization, I'm assuming the patient is on the top. Then we'll have some reflections that go from the patient back into the piezoelectric material of the transducer, and that's what we use to form our image. Then we also have some wave that is going into the back, and we have this acoustic backing down here. For most piezoelectric transducers, the backing represents a large part of the transducer. It represents most of the total volume or the thickness, especially for lower frequency transducers. And so the challenge here becomes, how do we effectively dampen or attenuate this echo in a small space without destroying the CT image? So what we found is, if you look at the different parts of the ultrasound transducer, the part that's not CT compatible is this acoustic backing. And its purpose is it has a high density or a high acoustic impedance similar to the piezoelectric material, so that it's well matched, and the acoustic waves that are in this piezoelectric layer go down into the acoustic backing. Then they're quickly attenuated and they don't travel back into the piezoelectric layer. And we need that because we need a short pulse to give us the high resolution for our ultrasound images. And so the problem is we need to greatly reduce the thickness of this acoustic backing, but we still need a short pulse. And so this led us to consider this idea of acoustic metamaterials, which is basically just an engineered material that has some property that's not typically found in the bulk material or typically found in nature. And so our material here, like many acoustic metamaterial designs, is just a simple periodic repeating structure. And the idea here is we wanted to make something that's like an acoustic diode, for example. So what if the acoustic wave could go from the piezoelectric material into the backing, and it could only go from the top to the bottom in this diagram. And then once it hits this interface with the air down here, it could be reflected, but it stays in this bottom or this back part. That's what we would like to have happen if we could make a design that could do that. And so here's one of the designs that we looked at, and the one that, as you'll see, we ended up building. And so you can see that it's the same idea that we show on the left here. In this case, we're building this cardiac array, so we have multiple piezoelectric elements here at the top. Then we have an acoustic backing, and this is still acoustically lossy. But now we have these triangular columns here, and this is actually a 2D structure, so it's like triangular prisms coming out of the plane of the board here. And so the idea of how this would work is you have some acoustic waves coming from the top. They encounter these triangular prism-shaped structures, which will scatter and redirect these towards this interface with the air. It hits the air, it will bounce back, but then it will hit the flat side of this triangle, and then it will kind of bounce around in the bottom part here. And so there's a number of different parameters, a number of different things that one could change in this design, and I won't go through all of the different parameters, but you can see there's different angles, different spacing that we could choose in designing the triangular prism-shaped structures in here. And these guys are filled with air so that they have a different acoustic impedance from this lossy acoustic backing material. So here's a video of one of our designs after we've chosen some parameters, and this is a video showing finite element simulation. And so at the beginning of this video, you'll see the acoustic waves, which have high amplitude right there. They're going down, they're interacting with the air-filled voids, and you can see that mostly just kind of spreads out the energy, right? So it's definitely not perfect. We have high amplitude here. It spreads it out. Some of it goes to the side, but some of it definitely goes back to the top here and back into the piezoelectric material. So it's definitely not perfect, but the amplitude at the beginning is much higher than the amplitude of the reflection that goes back into the piezoelectric material. And so we have some spreading out of that energy and some attenuation in the backing material as well. So at this point, we tried to build this device and build the transducer with these triangular structures as part of the acoustic backing. Again, I won't go through all the details here, but basically what we're doing is we have a multi-step casting process. And then we have these multiple rows of these triangular prism-shaped structures that are filled with this yellow wax. At the very end, we can dissolve that wax, and then they're filled with air. And so this is what our final transducer looked like. It's definitely not pretty. It doesn't look that good. But the question is, does it sound okay? And does it look okay to the CT scanner, right? And so what you can see here is you can see our air-filled voids here, this triangular prism-shaped structures that meet our specifications from the model that I showed earlier. So they have these very specific dimensions, and they have a 30-degree isosceles triangle angle here. All this extra stuff is extra wax or extra coating material from when we seal the transducer, but it doesn't affect the acoustic or the radiographic performance. You can see we have a nice 3D printed housing, so it looks a little bit better once it's in the housing. And the idea is that this device then could lie over the person's shoulder and it's on their chest while they're lying down inside of the CT scanner. So what is this thing? Yeah.
What is the frequency range that structure can do this? Is that very narrow, or does it have some bandwidth?
Yeah, that's a good question. So we have some bandwidth. At this point, I think the bandwidth is probably, it was about 3 megahertz, the bandwidth itself, not the center. So our center here was about 2.5 megahertz. So it's not totally narrowband, as you might expect it could be with these kinds of structures. But I think because of the combination of the design, but still having a lossy background material, we're able to have enough bandwidth that it's not only a narrowband material.
And what materials are acceptable in the CT not to create that artifact?
Right, so CT is imaging density for the most part, right? And so if you have something that has a density similar to bone, that's not ideal, but it's okay because obviously we have all kinds of bones in our chest. What we found, and I think this is on one of the next few slides, what we found is that if you use the conventional ultrasound transducer like I showed earlier, this thing has an acoustic backing that's something like 10 times higher density than bone. And so that's why it gives us this really terrible artifact. But if we can get it down like an order of magnitude or so and get it close to bone, then it's better and it could be acceptable.
Thank you.
So how well does this thing work acoustically? Well, we definitely don't have the really broad bandwidth of Dr. Olkan-Siemats here, but we do have an okay bandwidth for cardiac imaging. So on the left here is our acoustic diode transducer, and you can see that it has a slightly lower signal-to-noise ratio than this particular reference transducer. We have a few different control or reference transducers that we built to compare it with. In this case, what I'm comparing it with, which is this plot on the right, is a transducer that has the same thickness, but without those air-filled voids, without that acoustic diode in there. And so you can see qualitatively these look pretty similar. The main negative feature that this one on the right without the acoustic diode has is it has this extra reflection here. This looks pretty small, but when you display the ultrasound image with something like 40 dB dynamic range, then you can start to see these doubling artifacts. And so as you can see, the bandwidth is similar between the two. We actually have a little bit better bandwidth with our acoustic diode. Signal to noise ratio, we definitely lost some with our acoustic diode. And then the lateral resolution is similar between the two different cases. So the good thing is even with our lower signal to noise ratio, we've seen that we have been able to image in a human, in an adult. And definitely this is not the world's best ultrasound image of the heart. But we think it is the first one that uses an acoustic diode or an acoustic metamaterial. And as we'll show in a minute, we think that this transducer is also more CT compatible. So here you can see the IVS, the intraventricular septum, which is one of the main features we would need to track to assess the ability to determine the cardiac quiescent phase. You can see the other features. You can see the ventricle. You can see the valve here opening and closing. And then we could take that same data, we could look at the M mode like I showed earlier. So we move the transducer there. When we don't move the transducer, you can see this periodic behavior, which we might be able to use to gate the acquisition of the CT with a lower radiation to the patient. So what does the radiographic or the CT compatibility look like for this transducer? So the image on the left is similar to the one that I showed earlier. It's just a slightly different CT phantom. So here's a commercial ultrasound transducer. This on the right is our transducer that I've been describing. So it's definitely not perfect. We definitely still have some of these artifacts in here, but it's a lot better than this one that we started with. And like I mentioned earlier, we've improved the CT compatibility by about an order of magnitude in terms of the Hounsfield units. In fact, what we found at this point is that when we started here on the left with this commercial transducer or any version of this transducer that we could build, the main source of the lack of CT compatibility was due to the acoustic backing, because it's so much of the volume of the transducer and because the density is so high. But now with this new design, the source of the artifact is no longer the acoustic backing, it's actually the piezoelectric material at this point. So we think we have more work to do in that area to use a different material or to change the design. But now we're working on the active layer rather than, for example, the acoustic backing. So the other feature that we really care about is the acoustic performance. And so I mentioned earlier there's that reflection from the back wall that could produce an artifact in our image. And what we see is that if we use our acoustic diode design, we're able to reduce the amplitude of that reflection by about 70%. And so, again, it's not a perfect ultrasound image like we saw here, but we think it's acceptable for the gating goal that we have. So to summarize this part, we think that this is the first demonstration of a transducer that contains, as part of it, an integrated acoustic diode or metamaterial. We've shown that we can do in vivo cardiac imaging in an adult with a penetration depth greater than 11 centimeters using that device. And definitely this thinner transducer is not paper thin, right? It's still 7.5 millimeters. And most of that thickness or that volume is still the thickness of the acoustic backing. Only about 1 millimeter is everything else. Because we still have an acoustically lossy backing, we just have less of it to make it more CT compatible. And so I want to definitely acknowledge the work of my student, Stefan Strassel, who did this work. And he won an award for this at IUS in the fall. And also is on the cover of next month's IEEE Transactions on UFFC for this work. In the future, there's a couple of other things that we're looking at doing with this work. So far, I've really only talked about gating, and we're simply using the ultrasound to gate the CT acquisition. But what if you could combine them? What if you can fuse these two cardiac imaging modalities where you have the high contrast of the CT and the high frame rate or the high temporal resolution of the ultrasound? We've also been talking to some of our colleagues that work in radiomics or automated image analysis, and they've been pretty interested in this because whenever they look at CT images, especially CT images of the heart, they find that there's a lot of images that they have to throw out because the image quality isn't good enough. And so as we go from a world that's kind of the world that most of us have lived in and grown up in, where humans are doing all of this analysis, to the world where we just have so much data now and fewer images, fewer radiographic images of all kinds can be analyzed by humans, the quality of the images becomes really important, especially if we're trying to analyze a plaque burden or a degree of stenosis in a CT scan of a coronary artery, or trying to do that using AI, then the image quality and the other gating approaches become more important or more interesting to researchers in those spaces. So happy to answer questions about that part. If not, we'll go ahead and continue.
Yeah, I have a question about your parameter study on the acoustic diode. It's like my impression is like a smaller compared to wavelengths is always better, but is not that the case?
So the question is, why don't we make as small a triangle as possible, and that should be the best case, right? Yeah, so I think it gets a little bit tricky in terms of this type of material, and you're not only trying to make the smallest possible material, because in this case, the shape of the structure is actually helping us. And so I don't know if you can see that in this video or not, and maybe you can see it going in different directions when it interacts with the triangle. So if you make it small enough, then it's omnidirectional, right? The shape doesn't matter anymore. But that's not actually what we're doing at this point. So like you could see our dimensions, and it's not much smaller than a wavelength, right? It's more like on the order of a wavelength. And so I'm not sure I can say this is the ultimate best size that you would ever find, but this is a size that works and that worked best from the simulated cases that we tried. And I think it's because of that directional component. As long as you maintain some of that directionality, you can see what's happening. It's sending it more to the sides, or it's making it spend a longer time or have a longer path in the attenuating material. It's not just giving it like a Rayleigh scatter, for example.
So some directional feature is a little bit more affected than how many number of scatter there is in this design. Okay.
Yeah.
Thank you.
Yeah.
Is it possible to introduce like narrow waveguides in between the triangles just so you can try to limit the propagation of the wave?
Right, so what if we have something else in between here, I guess, is what you're saying, and then maybe you can control the direction more? So that might work. That's a good idea. I guess we also have to think about, do we have other reflections or other interactions at the boundary of those waveguides or whatever you're introducing? And so I guess that might be my concern, but maybe there's a way to do that if you have something like a gradual change or in the material properties, it just, that becomes hard to fabricate, right? Good thought there. Yeah.
Yeah, question about when we are doing the CT scanning, or like, should we put our transducer at the front of the CT scanner? Is there any way to like checking from the side? I'm not sure, like putting the transducer from the side, or like, is there any way?
Right. So where does the transducer go?
Yeah.
Like if we look here, where should the transducer be? And maybe we can put it in a position that would be more favorable.
Yeah.
Yeah, so that's a good point too. That's something that we've thought about. And so I think that this is not diagnostically accurate, right? Because you don't want it on the sternum. So it would be probably right here. But then you can imagine, I think this is what you're saying. What if I'm trying to image the heart and I have it down here and it's looking up into the plane?
Yeah,
So that could work. One of the things that we've found is that the logistics or the human factors of this end up being somewhat challenging. And so if you have a trained sonographer or someone who knows how to acquire a good echo image, they can easily acquire a good echo image. And they could probably even do what you're saying, which is if they're holding it with their hand, they can angle it and see the part that they want to see. But what we're proposing is not that, right? It's less human intervention, and you can't have someone in there holding it and like angling it. And so that's an important challenge. You can't have them in there when you're acquiring the CT scan. And so maybe there's a way to do that. We haven't found a way to do that yet because it's hard to find the right position and the right angle. And it actually can be difficult even when you're doing what I talked about, which is having something that lays right over the heart, for example. So it could be, it could work. It's just hard to find the right position, for example. Good question. Yeah.
So transducers with diodes, how much improved the image quality, the contrast resolution? Have you compared with diodes without diodes?
So how much does it change the ultrasound or the CT quality?
The CT.
The CT? So I can't tell you this is how much it changes the contrast. I guess we could calculate it from this phantom. Instead, what we quantified was what is the max intensity. So like what is the intensity of this artifact here versus over here. And so that's what we're showing here, that we improved that by about a factor of 10 or an order of magnitude. If we were looking at that and that's kind of the bad kind of contrast, then the background would be the same. So that kind of tells you similar information. In this case, I don't know that we have a target to look at to try to quantify the contrast or CNR though. Yeah.
So within the rectangular prisms, it's all air, right?
Correct.
So did you consider adding some material inside that results in more absorption rather than air?
Right, so what you're saying inside of the triangles, why don't we use something that's more absorbing there? So maybe I'm not understanding what you're proposing, but I think we don't want to do that because we need a strong mismatch in acoustic impedance at the interface between whatever this material is, and this is an acoustically lossy absorbing material, all of this other white stuff surrounding the triangles. So we want it to stay in there and be absorbed, but then here we want it to be directed, so we want to have that mismatch there. Does that make sense? Okay. All right, cool. Thanks for great questions. I just don't want to go over my time too much. So please raise your hand. Let me know if you have other questions. If not, I'd like to go on and think about what happens at the next stage. So we talked about what happens if we have this patient. They come in and they're complaining of chest pain. They could undergo a CT. And now what I want to think about is, let's say they undergo that CT for the diagnostic or the anatomical or the structural imaging, and their CT was conclusive, and we can see that there is a stenosis in the coronary arteries. Then what's the next stage? And so now what we want to think about is minimally invasive imaging or minimally invasive diagnostic procedures. And this is a person that would likely be sent to the cath lab if the initial testing shows that there is coronary artery involvement. So in this case, the question that we're now trying to answer is how do we determine who needs to be stented right away in order to prevent plaque rupture or myocardial infarction or any of those major adverse cardiac events that we've been thinking about. So overall, more than 1 million people are sent to the cath lab each year in the US. And then separately from that, there are 8 million of us in the US that have stable coronary artery disease. And that's basically the idea that, that we're walking around, we're seemingly healthy, we don't have any symptoms, but then occasionally, perhaps when exercising, we will have some of these symptoms like we saw in the poster or the brochure at the beginning of the presentation today, like we might have some chest pain when we exercise, for example. And so the challenge is, in all of these people, how do we determine who is at risk for myocardial infarction and who needs to be stented right away, and who can be safely deferred and does not need an extra procedure, basically. So currently, the gold standard for making that decision is something called FFR, or fractional flow reserve. And that's what this diagram on the left is showing you. So a pressure-sensitive wire is inserted into the arm or the leg of the person. Again, this is a minimally invasive procedure in the cath lab. And then that pressure-sensitive wire is routed to the coronary artery on the surface of the heart. And then the pressure is measured in 2 locations. One is downstream, distal to the stenosis, and the other one is upstream from the stenosis. If you take the ratio of those 2 pressures, that's FFR. And so if FFR is less than 0.8, which means a drop in pressure of at least 20%, then the guidelines say that the interventional cardiologist should give that person a stent. Now, ultimately, there are a number of other factors that come into play, and they can decide what they think is best on the basis of other risk criteria and angiography or other forms of imaging like we see down here. But ultimately, they have to decide, do they need a stent right away or not? The problem is in people that are deferred and are not stented right away, 10 to 12% of those people end up needing a stent or experiencing a major adverse cardiac event in the next 2 years after their first FFR. So it doesn't sound like a lot of people, but if we start off with millions of people, it ends up being a lot of people that are not stented when perhaps they should have been. So one of the challenges here is what is the technology that's available for doing this? And currently we don't have any technologies that can directly and simultaneously characterize this entire biomechanical environment that's surrounding that lesion or the stenosis. However, a number of different studies have shown that if you could look at the geometry or the morphology of the stenosis, the composition of the plaque, and the hemodynamics surrounding that plaque or that lesion, all 3 of those are independent mechanistic predictors of myocardial infarction and the likelihood of the plaque to rupture. So one way that you can do that, if you look at the hemodynamics, is to make a computational model of the artery itself. So what if using CT angiography, which we've already talked about, or using the catheter-based angiography, we could just get a really high-resolution image of the shape, the geometry of the stenosis itself, and then make a computational model of the blood flow through the stenosis that has that particular shape. So some of our collaborators at Emory have done that, led by Dr. Veneziani. And what they found is that in patients that have stable coronary artery disease and hemodynamically significant lesions, then if there's an increased wall shear stress in the proximal segment of the lesion, so that would be right here upstream from the lesion of the stenosis, or this red part right here in their computational fluid dynamics map, then if they have that increased wall shear stress proximal to the lesion, that's predictive of myocardial infarction. And that's additional incremental prognostic value relative to just the pressure measurement with FFR alone. So they can do this. They have shown this. The challenge becomes all of this is from a computational model based on only anatomical imaging. And in fact, when you're doing computational fluid dynamics in coronary arteries, the best results happen when you have more measurements, in particular measurements of the boundary conditions. And the way that you get those is with an invasive measurement. So you could use intravascular ultrasound or intravascular OCT, but you have to have a minimally invasive measurement anyway in order to make this model. At the same time, we said there's already more than 1 million people that are going to the cath lab each year. So the question that we then ask is, why don't we have an imaging system that can directly image all these things and make an imaging-based measurement to characterize the 3D lesion or stenosis environment? So we're working on developing this system or this catheter, and we call this the cautious catheter, which stands for composition, structure, and hemodynamics in intermediate stenosis. And the idea here is this person is going to the cath lab anyway. They're getting an FFR and an angiography. And remember, FFR is that pressure-sensitive wire. So why don't we also have an imaging catheter that can measure hemodynamics in 3D instead of just making these point-like measurements at 2 locations across the stenosis? If we could do this with a forward-viewing ultrasound device, we can look at the geometry in high resolution, we can directly measure the hemodynamics, and we can look at the plaque composition, because these are all things we can do using ultrasound. Then we could use this information, which is simultaneously dynamically acquired. So as the heart is beating, any changes in strain, for example, we can capture all those live using ultrasound, which is currently not a capability that we have, even though we know that all 3 of these are independent predictors of adverse cardiac events. Okay, so I'll show you where we are now with this system and this device. We're fairly early stage in development of this cautious catheter device. But right now, we are working with this current forward-viewing catheter device. So you can see a photo of our device, and now it's like we're looking into the face of the transducer. This is a fairly large device, so it's too large to use in coronary arteries. It's about 4 millimeters in diameter. However, at that size, we can use it in peripheral arteries, like in the femoral artery of a pig, which is data I'll show in just a minute. And so this is a forward-viewing 118 element ring array transducer. It operates at 5 megahertz, which is also too low resolution. And so the one that we build will be smaller and higher frequency for higher resolution. And right now we simply connect this to an ultrasound system, Verisonics Vantage, which is a research system. And like I said, it has some clear limitations, so we're limited in the spatial resolution and also because it's too big. But it can acquire these 3D volumes like we see here and help us work towards imaging intravascularly the 3D hemodynamics inside of an artery. So this slide here is just to show you how we display our images. I guess it's a little bit dark and hard to see on this projector screen. But the idea here is that we have this array, and this is the side view of the same thing I showed on the previous slide. It's looking down into the vessel. And in this case, this is just a tube in a phantom, for example. So it's looking down into the tube. And then whenever we have these small blue arrows that are pointing down, that indicates we have a negative VZ component. So along the main axis of the artery, the blood flow is going down away from the transducer. And whenever these little arrows move to the side, that's showing the other 2 components, the VX and the VY component. On the left here, it's only showing the mean VZ component. So this is like what you could measure if you only had a 1D measurement with a Doppler wire, for example. But we have more information in our measurement here. The bottom is the same thing, just with a faster flow. And so you can see at some time point, the flow will reverse, the blue arrows will point upwards and become red. But it's just showing you how we're displaying our imaging data. So we use the same device to image in the femoral artery of a pig. And so here you can see us doing our in vivo study. Here's our catheter-based array. It's going into the pig's femoral artery. And again, on the left here, this is the mean VZ component. So the mean component along the long axis of the artery as a function of time. And then on the right, we're showing the synchronized imaging data. So sometimes all those red arrows point upwards when we have blood flow towards the transducer. And we've got about 2.5 cardiac cycles here. But hopefully what we can appreciate is that we have a lot of complex blood flow dynamics that are happening, right? That we can't necessarily see when we only look at the mean VZ on the left. So we could do this for multiple cycles, and we could see, for example, if we look at time point B and time point E, they look very similar if we're only showing the mean velocity versus time. But if we look at the corresponding images, then they look very different. It's just that all this information got averaged together. So we think that this is the first intravascular measurement of 3D blood flow dynamics. And again, what we're looking at here is we have this forward-viewing ultrasound array. In this case, it's looking down into the artery of the pig. And we're showing 3 different synchronized planes here. So this is 10 millimeters away from that device, from the face of the transducer. The middle one is 12 millimeters, and then the bottom one is 14 millimeters away from the face of the transducer. You can see that they look similar, but hopefully if we look closely, we can appreciate that they're not exactly the same. And so I can stop this movie, and you can see that they're similar at these different locations, but they're a little bit different, as we would expect, because what we're thinking about it is just the blood is flowing from one plane to the next, right? So it's going to be very similar, but at one snapshot, at one time point, it's going to be slightly different. This is a 3D data set, and we do have all 3 components of the blood flow. And so we could reslice this in any direction. We could look at just the short axis views, which is what we're seeing here. Or we could look at along the artery, for example. We could slice it this way. And that might be what we would want to do if we wanted to look at the wall shear stress, calculate the wall shear stress, or the tangential force of the blood on the wall of the artery or on the plaque itself, which is what we actually care about. So one of the questions that you might be asking is, if we're measuring hemodynamics, but we're measuring hemodynamics using the catheter or using the device itself, then won't the presence of that device affect the blood flow dynamics? And so the answer is it could, but it depends on how we design the device or how we design the catheter. And so we've looked into this question in simulations and also experimentally. And this slide is only showing the experimental results. And you can see the experimental setup here. We have this large high-frequency external array transducer. There's some ultrasound phantom down here that has a stenosis. And then there's some tube that gives us some flow through this thing here. And so what we have found, for example, is if we don't have a catheter inserted into this tube, that's case A. And then in case B, if we insert a catheter that looks like this one on the bottom left, where it has these openings, it has a hole in the middle to allow blood to flow through it, then the effect of the catheter itself on the blood flow is very, very small compared to any stenosis that's in there. So we can look at these two images. They're almost exactly the same. We can plot the cross-sectional velocity through the middle of these, and we can again see that they're almost exactly the same. So if we can design our forward-viewing imaging catheter in the right way, we think we can still accurately estimate the hemodynamics using an ultrasound approach. And so this question of what is the best strategy for estimating the blood flow velocity using an intravascular forward-viewing array is still an open question that we're looking at. We've looked at a few different approaches, including a speckle tracking or a particle image velocimetry approach and a Doppler approach. We can compare those, in this case, with the analytical solution because it's just a straight tube. In some cases, we compare those with the computational model, with the computational fluid dynamics. And so what we've had to do is go very slowly, start with the straight tube, then go to a simple stenosis, for example. And then in that case, you can see on the right, we've overlaid our wall shear stress map onto our B-mode ultrasound image. And in this case, what we're thinking about is this particular geometry where we have the blood flow mostly going towards or away from the transducer, which is a little bit different geometry than what people have done with ultrasound to look at wall shear stress in the past. And so now we're going from these simple stenoses to, for example, if we get a patient-specific geometry from a CT scan, and then we can 3D print that and make a phantom of that as well, compare the CFD, the computational fluid dynamics model, with the ultrasound measurements. But I don't think we've determined yet what is the best ultrasound approach for measuring this. Of course, the most important and maybe most interesting part is how do we actually develop this device? We need to build a smaller, higher frequency device that is something like 1.3 to 1.5 millimeters in diameter to do all these things that we've been talking about and that we've been showing with the larger device in the pig. So here's our current design, and in this design here, I'm just showing the tip. So this is a little bit less than 1 centimeter. This first segment here, that's just the solid tip that's a little bit stiffer than the part at the back where we have all of our cabling and our mesh components of the catheter. And so the way that this will work is we have multiple flexible interconnects here that we bond together. Here you can see the distal end of that interconnect, so that's this part down here. We align and stack those up and bond them. And then on this end here, this front surface is where we build our array. You can see the cross-sectional view of that with the traces. And so this thing is lapped and polished, and we build our array on that surface. So this is definitely a challenging project. And we're still in the first year of this project, but we're excited to get more results and do more of these multifunctional measurements. So for the most part today, I've only talked about the hemodynamics. We're also interested in, for example, overlaying the hemodynamic information with, for example, elastography. And does that give the interventionalist more information about a specific region that might be a region of interest or concern during the procedure? Once we've developed this device and our imaging strategies, then we plan to test this with our collaborators in cardiothoracic surgery at Emory. And what Dr. Padala's lab has demonstrated is that they can control the degree of stenosis, so they can mechanically alter the stenosis in the pig, and then that in turn affects the hemodynamics. And they've also seen that by controlling the degree of washout or recirculation, if they then go back and look at the histology, they see a different plaque composition in those animals. And so we think that will give us a good test platform for this particular device once we have developed that. So in summary, we've shown, I think, the first proof of concept of 3D intravascular velocity estimation which was in the femoral artery of a pig. And then we're proposing to take that idea and develop a smaller, higher resolution device, which will allow us to simultaneously look at the hemodynamics, the biomechanics, and also the structure or the morphology of that lesion, and in a real-time and dynamic way. And we envision that this is a device that would be used in the more than 1 million people that are already undergoing these minimally invasive procedures in the US each year. And my student, Sunny Kim, was the person who did most of the blood flow imaging work in this project here. So any questions about this part before we go on? Yeah.
Yeah, first of all, this is really cool concept and really like that design. But from your first prototype, your final device is smaller than that, so you're expecting like a higher frequency shift to the higher frequency, or you want to keep that 5 megahertz?
Yeah, that's a good question. I don't think I said the frequency. So we're designing this to be about a 30 megahertz frequency, wow. So it's really, really high. And so you can see there are a lot of challenges in building this thing, and that's what we're working through right now. Fortunately, we have some time because we're still in the first year of this project. But the challenge in determining that frequency has been kind of a continual discussion of what the needs are. So whenever we talk to, in some cases, the cardiothoracic surgeon, or in some cases, the interventional cardiologist or the interventional radiologist, we will get different feedback. And if you talk to different interventional cardiologists, they will often tell you something different. And so some people really want OCT, not ultrasound, and some people say both. And so that's actually the most common answer that we've gotten is, well, I need ultrasound to see see into the wall, to see something about the shape, and to be able to do more, have more information about the composition or the characterization. But then often the same people will also want the high resolution surface features or surface anatomy of the OCT. And so this 30 megahertz that I said, maybe it will not make them happy when we have that final device, because some of them will want lower, some of them will want higher. 30 is maybe similar to the side viewing, some of the side viewing commercial IVUS devices that exist now. But I think that's the challenge is what is the right frequency? What is the right frequency for this scenario? Where obviously we're doing forward viewing, so it's not the same distance as when you have the side viewing IVUS, right, that's seeing directly into the wall. So for that reason, we might want it to be lower, but often when you talk to an interventional cardiologist, they will say, no, higher resolution, we need more resolution. So that's kind of why we ended up there.
Okay.
So guessing with the high frequency, it's difficult to do a velocity estimation, like phase estimation, right? So are you using speckle tracking to get the 3D velocity components?
Yeah, so we've done both, and that's kind of what these slides were about. So on the left, this is the speckle tracking, and on the right, this is a Doppler. And so these images, for example, are a 23 megahertz forward viewing array, but it's not a really small array because it could be larger for these first experiments where we're just looking at the kind of thing that you ask about, like at this frequency and in this forward viewing orientation, what is the best way to do this? So for the things that I showed earlier that were in the pig, they were at a lower frequency, and we did use a Doppler technique for that. So we did Doppler with transverse oscillation to do that. But I'm not sure we know the final answer as to whether you want to do PIV or speckle tracking or you want to do Doppler. Yeah.
Yeah, I have several questions. First one is I saw that the transducer is like a ring, right? So how did you measure all the velocity distribution in a circle? That's one question. And second is I saw you have a transmit element and a receive element, right? So what's the design idea for that? And the last one is you say you use a 7 event compounding. So can I ask more detail?
Sure.
Is there any beamforming you use for the EVG? And the last question is, the transducer look like a forward-looking. So how did you get a wall information? Because suppose like a volcano system is kind of side-looking. So that is
right. So I'll try to answer some of those at once, and you can tell me if I didn't hit all those. So you're right, this is the forward viewing ring array. There's advantages and disadvantages of that. Like we've said before, we need a guide wire for this thing to be delivered on. So we need some opening, whether it's this or the design I showed on a later slide where we had still a hole, but maybe a smaller hole. We always need to be able to deliver it with a guide wire. I think your other question was, how does this work when we have two rings? How do we make an image of anything, or how do we estimate the blood flow? And we just have to think about the point spread function. So what does the beam or the point spread function look like when we do the focusing with an array that looks like this? I don't think I included that slide today, but if you want to, I can probably find the image later that shows the point spread function for this array. I think it is in the paper when we publish this. And so what we should think about is, if we're acquiring this 3D volume, then we can form a beam right down the middle of that 3D volume, but we can also form a beam over to the side, right? Because we can steer. So definitely when we steer, we have more off-axis energy, or we have a higher side lobe level, but we can steer a beam to kind of any location inside of our volume. Does that make sense? So like we have side lobe contributions or a non-ideal point spread function in every case, and the ring is not necessarily helping that, but having two rings is much better than having one ring in terms of the point spread function. If you think about taking the Fourier transform of this guy, for example. So we can, in fact, measure it in all these different locations. We just have a slightly different spatially varying point spread function. And then what were the other questions? It was, how does it compare to the side viewing volcano geometry?
Yeah, like this slide, you show this 7 steel plane wave.
Oh yeah, how do you do the beamforming in the plane wave
Just
compounding?
fire all the element, or you have to, for linear array, they need an angle. So I just asked about your transducer.
Right, so in this case, because we're using Verisonics, one of the ways that it works best is to have either a diverging wave or a steered plane wave transmit event, and so that's what we did. I don't necessarily claim that this is the optimum way. And one of the things that we've discussed and been having to look at more recently is perhaps you need a combination of transmit events or different ways of doing the beamforming, because maybe what we actually want to do is do it really fast at the beginning like we did here. So what we did here was we transmit with all the elements at the same time. And so there's 7 angles. So like angle 1 will be something like this. I don't remember the numbers, and it's in the paper as well. But it's -11 degrees, then it's -7 degrees, then it's -3, then 0, then +3, then 7, and then +11. So we're doing something like that. And that's how we get all of our data. And then we compound those together, which helps us with the noise in B mode, but especially in the noisy Doppler data that we're dealing with there. But we could do it any number of other ways, including maybe we want to first do it really fast, like I was saying. And then maybe once we get a sense of this, so if I show some of these other slides, like maybe we want to first do it really fast to get a rough image. And then maybe we want to go through and do a focused transmit event instead of plane wave, because what we really care about here is having an accurate estimate of the blood flow velocity profile. So then maybe if we only care about this line right here, we could have focus beams that go across just right here to get a better estimate of just the velocity profile there. But I think that's still an open systems question as well.
Thank you.
Yeah.
Could you talk a little bit more about the elastography applications that you were envisioning for the future? I'm assuming you're not going to be doing like a artifact citation using this particular transducer design or anything. So I was kind of curious about where you were thinking of taking that. What kind of direction you were going to be taking that.
Right. So we could do a passive strain elastography, for example. That's basically what we're thinking.
Okay. Okay.
Does that answer your question?
Sure. Yeah.
Okay, we could talk more later.
Sure.
Okay, so I know we're probably close to the end of our time. I wanted to talk for a few minutes about our work in kind of the third stage of this process, or when that second stage of minimally invasive imaging becomes more difficult or more challenging. So we've been thinking about that patient. The patient arrives at the ER, they have chest pain. Maybe they undergo some frontline testing like ECG. They might undergo that CT to look at the anatomic structure of the stenosis. And then some patients will end up in the cath lab for minimally invasive testing or minimally invasive diagnostic tests. So now what we want to think about is what happens in the patients that are in the cath lab. They're trying to undergo FFR, the catheter-based forward viewing ultrasound imaging like we've been describing, or just catheter-based angiography. What happens in the cases where you can't route a catheter or any device to the location that you care about in the coronary artery because you can't even route the guide wire itself. And so the reason why that could happen is if there's something like in the image that I'm showing here on the right, if you have this heavily calcified chronic total occlusion, where almost the entire artery is filled with this calcification, and then there's only this small remaining lumen in the middle of the vessel, then it's really difficult to do any of these things. It's hard to do a diagnostic procedure. It's hard to pass a stent or a balloon or do anything, because on the way to either the coronary artery or on the way to a lesion in the legs, for example, if you're trying to revascularize a major artery in the legs, it's fairly common to encounter these. And if you encounter a CTO, then about 20% of those cases will fail because they can't advance even the guide wire, let alone another device, beyond this heavily calcified occlusion. And what we should think about here is that this occlusion is not the symptomatic occlusion that we care about. It's just an obstacle along the way. In most cases, these people have these CTOs that develop gradually over time, and so they would have a lot of collateral circulation. And so this lesion itself is not the one of concern. It's more like the plaque that we need to get to that's in the coronary artery, or if it's in their legs. Some of these people will present with numbness or like their leg is turning blue from this other downstream lesion. And we can't get to that lesion unless we can first get across this calcified occlusion. So we have to route the guide wire or the procedure fails. So in that case, there's no catheter-based ultrasound device or other device that would really help us, because we would need something even smaller. So here what we're thinking about is how the interventionalist, and this is typically an interventional radiologist, would do this procedure. And this example is in the legs, but it could be on the way to the heart as well. And so here you can see an artery in this 2D side viewing fluoroscopy image. You can see the artery going down, and then it stops. So there's some occlusion in here, and then we see the artery continue again. And so somehow the blood and the dye in that blood was communicated into this lower artery by these collaterals, but there's clearly an occlusion here. And so what the interventional radiologist has to do is they have to route the guide wire from here down to here, only looking at this image. And what they're trying to do is push the wire into this tiny hole right here, but they can't see this image. They can only see this image on the left. So imagine a person who's pushing a wire with their hand from the top part. They're trying to get the tip of the wire into this small hole and then link up with the bottom part in order to revascularize some lesion that's somewhere down here. So you can see why that would be hard and why that would be challenging. And so for that reason, we're proposing this other system that has the guide wire itself that contains forward viewing imaging. So before, the things I've been talking about with the catheter had, for example, a 4 millimeter catheter, and that was the larger one that we used in the pig. And then I talked about building that about 1.5 millimeter coronary artery catheter as well. Now what we're thinking about is the guide wire itself has the imaging. And so what if the guide wire can transmit and receive? It can image all the time. It's robotically steered, and so it drives around inside of the artery. It can then see these occlusions, and it can go around them. And the way that would work is by having the ultrasound transducer on the tip of this guide wire. But the guide wire itself is much smaller than what we've been talking about. So this is an 035 robotically steered guide wire that we're showing here. And so 035 guide wire is 0.88 millimeters. So this is less than a millimeter device. And this is the wire rather than being the catheter at this point. You can see the ultrasound transducer, which is just the tiny tip. And here we only have one element. This is a single element transducer. And the way that this works is that this robotically steered guide wire, as you can see the tendons here, has multiple degrees of freedom. So you can see it has the distal and the proximal joints here. It can be steered at each joint in multiple directions. And then we use a synthetic aperture approach. So we're acquiring data all the time. And then as that data comes in, we use that to form an image. And this was our first prototype device that we built in collaboration with J.W. Desai's lab at Georgia Tech. And so they're the robotics group that does all the steering of this steerable guide wire. Okay, so our first device has this 16 megahertz forward viewing ultrasound transducer. On the left, you can see what happens if we steer the robotically steerable guide wire across the wire targets. So we can see the white wire targets in the black background. And then the right shows using the same approach, but if we steered it in two directions to image an ex vivo artery of a pig. And here we can see some of the structure in the wall of the artery. But again, this is just an ex vivo artery at this time. One of the challenges that we've encountered, and when we talk to the interventionalists that they often mention, is the challenge of how do we deal with these two different images or this scenario where we want to be able to see both of these things at the same time. So we would like our imaging system to be able to have high enough penetration depth for example, to be able to see through or around these long occlusions, but also we need high enough resolution to see these really small paths or channels through the occlusion. And so what we would like to be able to do is obviously we would like to have an array, we just don't have a lot of space, or we would like to be able to in some way have a high frequency or high resolution and also a high penetration depth capability. And so the way that we're trying to address that or get around that is to build a single device that can operate at multiple frequencies at the same time. And so the reason why we have to only have a single device is because we don't have very much space. So we only have room for one electrical cable or one electrical connection in our steerable guide wire. And part of that is because we have those mechanical steering tendons that take up some of the space inside of that guide wire as well. So here's our design, and this is a piezoelectric element that operates at 2 different frequencies. So you can see the outer ring is the low frequency part at about 33 megahertz. We have this inner circle, the inner annular element that operates at about 17 megahertz. They could be any frequencies. And then we have this isolation notch or cut that we make in between them. On the left, we can see the cross-section of this. We start with the bulk PZT device. Then we use laser micromachining to remove some of the material, and that's how we make the 2 different thicknesses. We cut this isolation notch with the idea being to reduce the cross-coupling or reduce the vibrations between the high frequency on the outside, the low frequency on the outside and the high frequency in the middle. Then we metalize and we add our acoustic backing, and then we mount that device onto the end of that robotically steerable guide wire. It still only has one electrical connection here. You can see the image of this, the photo with the microscope scan overlaid. And so in the middle, this device, which is the high frequency part, is about 65 microns thick. Then if we go to this notch, it's only 48 microns thick. And then the thickest part is the outside that's 125 microns thick. And the way that this thing works is it could simultaneously transmit and receive at both of those 2 frequencies. So we can characterize it electrically using an impedance analyzer, and we see that it in fact has 2 different resonances at the same time with only one connection. And then we can characterize it acoustically as well. And so we see that if we transmit and receive using a broadband pulse, we have 2 different peaks, and both are somewhat broadband. Clearly, we're less sensitive at this higher frequency, and so that's an area where we need to do more work to get the sensitivity to be higher at this higher frequency. But if we take the acquired echo and then we do digital filtering to separate out the low frequency and the high frequency pulse, we get 2 different pulses, and again, these are acquired at the same time. So that would allow us to make 2 different images at the same time. The high penetration depth image, which is the top one in A, for which we're showing the point spread function here. And then the high frequency image on the bottom, and that's our 32 or 33 megahertz image. So what we're doing here is the transducer, the steerable guide wire is on the left, it's imaging a wire target, and then it's steered across the wire target to see the point spread function. We have about twice as high resolution with the higher frequency device as we would expect. We can also image the ex vivo pig arteries using the same device. And here what we're looking at is the cross-section of the arteries. So we see the top and the bottom walls here. We have higher penetration depth at the lower frequency. At the higher frequency, we can resolve some of these features, like in this case, the calcification in the wall of that particular artery. Okay? And so the way that we envision this thing would be used eventually is that we would take these 2 different simultaneous images and we would combine them, or we would fuse them into one. And so, for example, we could use the high frequency information until we run out of high frequency information. You see that happens down here. And then after those first few millimeters, we could fill in with the low frequency information. And here's the fused image. On the right, we're showing the fused rotating images as well. And so the blue is the high frequency, the gray is the low frequency. But like I said, we think we would just fuse those together because the interventionalist doesn't care what they're looking at. They just need high resolution close to the transducer, but higher penetration depth to plan the trajectory of where that guide wire would need to go to make it all the way through that calcified occlusion. So to summarize this part, we've shown the first robotically steered guidewire-based imaging system, which is part of an 035 guidewire or a 0.88 millimeter guidewire. We've also shown proof of concept for a guidewire-based imaging system operating simultaneously at 2 different frequencies. And that was the last part of our process in describing how we could use ultrasound to make a safer, more functional, more diagnostically conclusive process for the patient that presents complaining of chest pain, right? So we talked about frontline imaging, or how do we determine coronary artery involvement. and we said CT plus ultrasound together. Then we talked about minimally invasive functional imaging, and that's when I talked about the forward viewing multifunctional catheter looking at this hemodynamics. And then finally, we considered what happens if we can't place a stent, we can't route a catheter, can't do anything because we can't even route the guide wire. And that's where I showed the last system, which was the guidewire-based imaging system. So I'd like to thank you for your time. I'm happy to answer any questions. I'd like to thank my postdoc and all my grad students, and they're the ones who did all the great work here. So thanks for your time, and happy to answer questions.
Yeah, the last one is also very cool. And but the motion seems like a little bit more complicated compared to wobbling or rotation, which means every single transducer get the signal with like a 6 degrees of freedom will be determined first and then get the signal. So
Right.
imaging rate probably really low. What is the average like frame rate of that speed?
Right, that's a really good question. So a couple things there that I'll comment on. One is just how do we do this and how do we form the image? And so I'll show this movie here since you were talking about the degrees of freedom and how this works. We actually do a calibration before we acquire the images, and that's how we know the position of the sensor or the transducer element. And so you can apply the same force to the different tendons repeatedly, and then you can know the position of the transducer element. And so that's how we do the beamforming, because we know where the tip is based on prior measurements. And then I think your question was about the frame rate. So what is the frame rate that we can achieve? So like most things, the answer is it depends, right? It depends on what is the distance you need to sweep out. Do you need to do one? Do you need to do two? Are we doing a raster scan? In general, what we have concluded is we can do a scan in about 1 second. You can definitely do a 2D scan in 1 second. You can do a slightly more sparse 3D scan in about 1 second as well. If you wanted a really dense 3D scan, then it would take 1 second times the number of planes that you have. But if we want, say, only a few elevation planes, then we can throw out some points in the first plane, and we can also do that in about a second. And so, depending on your point of view, maybe that's too slow, but we think it could be okay. And talking to interventionalists, the image that they have to work with right now, they can't see it at all. So we think this could work if that's the current time delay. But you're right, that's an important consideration.
Thank you.
Yeah.
That's a very good idea. You use two frequencies. So the lower frequency, you want to increase the image depth, right? So why you just put your transducer tip a little bit forward, and then you can use one single element high frequency.
Right, so we might be able to do that, you're right. In some cases, we absolutely might be able to do that. Just move the transducer closer to whatever you're trying to image, and that could totally work. The challenge is, in some cases, you can't get it beyond the occlusion, and maybe this may not be visible from this one here because I'm only showing the 2D slice. But in some cases, your occlusion that you're trying to get through is very tortuous. So it's not necessarily like once you get the tip in here, then it's a straight, smooth pass all the way through. Yeah. So it's helpful to be able to see what is the tortuous nature of that channel before your device is pushing right up against it. And that can allow you to plan the trajectory if you have some complicated path that steerable guide wire will need to take.
Okay, thank you.
Yeah.
So are you using some kind of a shape memory alloys for that guiding mechanism?
No, we're not. But maybe that's something that should be considered in the future. So we're just having these tendons, and then they're deforming it. Question?
Impressive work, and as I'm aware, there's a lot of computation that needs to occur once you acquire volumetric data. What does your processing pipeline look like? How long does it take to go through to render 3D?
So you're asking about for this part, for this last part that I showed?
I guess the second part where you're showing the flow data as well.
Okay, yeah. So how long does it take to produce the 3D volumes of the blood flow, for example? Yeah, so we can pop up an image very quickly if we want a 2D plane or two orthogonal 2D planes. And so we have a system to do that. But if you want, this is the 4D data, we're still doing that offline. So I'm not sure that I know, this is how long it takes to make the 3D movie. I guess that's the part that we, at this stage, don't worry about as much, because we're not as much on the visualization side of things. But you're right, that's an important concern if we want to display it in 3D, if we want to pop up a 3D visualization. For now, what we do is we can just show different 2D planes. So I don't think we have totally solved that question.
Sounds good. So in lieu of time, let's thank our speaker.